Hello and welcome again to my physics online video lecture series. Today's video we're going to be talking about engine efficiency. So this is a continuation of our discussion of thermodynamics and specifically of the first and second laws of thermodynamics. Today what we're looking at is how to define engine efficiency, which in some sense also gives us a way of defining things like refrigerator efficiency. For those following along in the context of the second law of thermodynamics, you know that I have given a few different statements of this law. One of them is the engine statement, another is the refrigerator statement, and of course there's also an entropy statement, which we're not so much interested in today's video. So we're going to focus mostly on engine efficiency today. You'll recall that we have up to this point discussed a few different thermodynamic processes, and we have discussed the first law of thermodynamics, which says that the heat that goes in is equal to the work plus the delta E of internal energy, the work that the system can put out times plus the internal energy change. Now, worth noting at this point is that different people use different notations. I introduced H as the symbol for heat. A lot of textbooks actually like to use a Q for heat, and so sometimes we put Q in is equal to work, and then this delta E, this was change of internal energy. You could use a delta U here. The other thing that you could use is the fact that this internal energy is reflected by temperature changes and phase changes. So you could also say this is the work done by the system, and so you can put a subscript of an out on the W if you'd like, plus, for example, C times M times delta T plus maybe M times latent heat, something like that. Second law of thermodynamics, we had several different statements of it. Essentially, the statements can be said along the lines of you can't make an engine that is 100% efficient, you tend to increase entropy within your system, etc. So the other end of it is, what is an engine and what does it do? And for that, we also have to know that there are various thermodynamic processes. And these various thermodynamic processes kind of govern how a system operates. So you can operate at constant pressure, which is isobaric, constant temperature, which is isothermal, constant volume, which is isochloric, and then just to stick with the motif of constants, we could say like constant heat, which really just means no heat transfer in or out of the system, and that is, of course, your adiabatic system. So, and then, of course, you have like PV diagrams that can go with each of these. So PV diagrams, which might be associated with each of these processes. And this is all kind of like the background information to today's topic, which is engines and engine efficiency. And the basic idea behind engines and engine efficiency is to make an engine, a heat engine, you're making use in some sense of this first law of thermodynamics, in which you are bringing heat into your system. The result is that the system is able to do some mechanical work, and then there ends up being some rejected heat. You could call it like waste heat or discarded heat or rejected heat or what have you. And so what that may look like as a diagram is this. You have your hot reservoir, which is where you're kind of like drawing your heat from for your system. So it's at temperature high. So this is like the high temperature reservoir. And from this, you are basically pulling some amount of heat. And we can label that as either H high or Q high or something like that. I'm going to label it as Q high in following most textbooks. And I maybe should mention here, for what it's worth, H in this equation is heat, but often used to represent another term called enthalpy. Ergo, why I'm switching over to using Q here. So the high temperature reservoir provides some heat to our system. And so basically, like, heat is sort of flowing this way, if you will. And then the system has some amount of work that it does. So we could represent that as like W. This is like the output work. And then there's also some amount of rejected heat. We could call this QC. And that in turn is basically going into a low temperature reservoir. And your low temperature reservoir then is just like your wasted heat. So low temperature reservoir. And often that's at temperature TC. Now, in the context of a PV diagram, what might this look like? Well, that actually kind of depends on some things. There is a Carnot cycle, there is an Otto cycle. They're not exactly the same. The Carnot cycle is sort of like the most efficient possible engine, and then from that comes your second law of thermodynamics. But a possible PV diagram might look like this. So here's your volume, here's your system's pressure, and then since this is the system pressure, essentially we expect to kind of like heat at constant volume. So like this, for example, is a possibility. So this is constant volume heating. This would be your QN, your high temperature reservoir supplying heat to your system. And then essentially you have an adiabatic expansion. So for a vehicle, this would be like the power stroke. And so this, kind of comes down here. I'm not drawing it very well because I can't hand draw very well, but essentially you end up with something like this. Then you have to allow some rejected heat, like this. Again, you want that at constant volume. So this is your rejected heat leaving your system. Then you have to compress your basically your engine back to your starting point, and so you do that hopefully adiabatically. So this right here is adiabatic expansion, and this is adiabatic compression. And this system that I've drawn here basically represents what's called the Otto cycle. Not Otto like automobile, but Otto like the name Otto. And so this is your PV diagram for that particular cycle. And then this area kind of bounded by this system that we have here, that we've drawn here. Like if I were to draw in a shaded area, this shaded area represents work that's being done by your system. Okay. And you could say that this right here is basically like heating at constant volume. So if we wanted to add some more labels here, this is heat at constant volume. This is cool at constant volume. So these are both isochloric processes. All right, so you may be wondering, like, how much efficiency does an engine have? And I usually use an eta for efficiency, or a mu. So let's say efficiency of engine, and that can be represented by eta. By definition, your efficiency is essentially what you get out divided by what you put in. So that would be the work out divided by the heat in. Okay, so that is by definition true. Now, parenthetically, we know that the work out from the first law of thermodynamics basically has to be given by the heat that goes in minus the change in internal energy. So you could say like minus E internal, but that E internal is like you've heated the system up and now you have to cool the system down, and so that would be sort of like rejected heat. Okay, so that ends up being QH plus QC, and that in turn ends up being QH minus QC. Basically, the claim here is that this term right here is a negative, and so this is like subtracting a positive. All right, so in the context of this being QH minus QC, you can always have QH minus QC, and you know, QH minus QC divided by QH is going to be 1 minus QC over QH. And so sometimes we write that as 1 minus QC over, QH. Let me just put the absolute value around the whole thing. So that is your actual efficiency of your engine. For refrigerators and therefore for air conditioners, there's actually a similar concept. So this is efficiency of engine. For what it's worth, a refrigerator has what's called coefficient performance. And the coefficient of performance, or sometimes called performance coefficient, is often represented by a K or a kappa, and that, for what it's worth, is given by this process basically in reverse. Essentially what you have to do for a refrigerator, you'll recall, is that you do work into the system to move heat from the cold reservoir into the hot reservoir. And so this ultimately ends up being given by QC divided by QH minus QC. Okay, and so that is kind of your nearest equivalent, or maybe I should say that is your analog for a refrigerator. Let's end with a brief example. So you have a certain engine which is burning gasoline. It does 3,000 joules, or it takes in 3,000 joules of heat from the hot reservoir, basically from burning the gasoline, in order to do 600 joules of work. We want to know what the engine's efficiency is. So again, eta is defined as the work done divided by the heat borrowed from the hot reservoir. And we just simply have those two numbers given in the statement, so that's 600 joules divided by 3,000 joules. 6 over 3,000 is a fifth, so that is 0.2. That is equivalent to 20% efficiency. And that's all for today's video. Hope you learned something from it, and thanks for watching.